Ah. Ah. Hola, hola, hola. Está bien.
Elle a oublié de brancher le terminal du micro, donc du coup, voilà pourquoi ça marche pas.
Ah non, mais c'est bien, c'est parfait.
Voilà, voilà. Vous êtes dans notre zone?
Non, pour le moment, j'ai 3 micros là pour les jurys et ça marche. Normalement, si tout va. Pour le moment, ça doit marcher. Voilà. Non. Ah oui, voilà, voilà, voilà. D'accord.
Donc, si besoin, il y a quand même des personnes à bureau ici. Voilà, vous demandez au poste de sécurité. D'accord, moi, en D126. D126, à côté de la barrière. Voilà, exactement. Voilà. Il y a mon collègue, donc n'hésitez pas.
Ah, parfait. Merci beaucoup.
Bonne séance.
Bonjour. Bonjour. Hola, hola, hola. Bonjour. Ça marche? En deux, en deux. Super. Bonjour. Uno, uno, uno. Bonjour. Hola, hola. Bonjour. Joder. Bien. Hola, hola, hola. Hola, 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 hola. Hola, hola, hola. Hola, hola, hola. Hola, hola, hola. Probando. Uno, uno, uno. Tu peux pas charger en même temps que tu filmes. D'accord.
Mais j'espère.
Bon, tu peux t'asseoir ici, Agustin, avec l'ordinateur. L'ordinateur, maintenant, il est en transmission.
D'accord.
Donc, normalement...
Juste pour le. Je fais comme ça et tout va être là.
Oui. Bon, je vais voir ma copine. Si
Oui,
tout va
oui.
bien, je reviens.
D'accord.
Merci beaucoup.
De rien. Bonjour. Oui, oui, c'est ça. Mais ça commence à 14 heures. Ouais. D'Allemagne. Ah non, non, c'est à Paco. Oui, oui. C'est son ordinateur, il fait un live stream sur Internet. Tu as un copain? Le chef, sa copine, organiser des trucs de côté.
C'est Gérard.
Philippe. Ah.
Tu fais tes études ici aussi?
Oui, oui, j'ai commencé en octobre.
C'est l'intérêt?
Ouais. Non, le premier. Donc c'est mon premier. C'est le plus grand. Ça va pas être rempli.
Son pas comme todas las leyes, pero es normal.
Paco.
Ah, perfect. Yeah, it's perfect.
You will be here. And
Yeah, yeah. Maximum. Yeah, till the 1, 2, 3, 4, 5th chair is okay because I won't move beyond the 5th chair. It will be between here and here maximum.
Okay.
Yeah, that's okay.
But you're quite small on the picture. But I can zoom to you more, but then we don't see this.
Keep straight.
Okay.
Fix. Well.
Tu veux que je check si ça marche en streaming?
Normalement, le streaming, ça marche, c'est avec l'ordinateur.
Ça, c'est les vidéos et ça, c'est le streaming.
Ah, ok.
Et après, il y a un caméraman.
Mais peut-être la caméra, il faut qu'il soit uploadé.
Sí, sí, casi, casi. Ay, Dios.
Vaya, chaval. Esta tarde no está.
This afternoon finish. Joder, había 14 y se ha caído Flor Margot. Porque no eran night, ¿no? El director de mi departamento. Pero bueno, yo le he puesto botellas de agua. ¿Quiero una botella de agua o no? ¿Sí? ¿Quieres? Normalmente ahí.
Qué guay.
Thèse expérimentale sur
Sur les bois aussi.
Non, non, c'est le stockage des déchets.
Des déchets.
On peut mettre
Dans la roche.
Oui.
Comme le CO2.
Oui, oui, comme ça. Non, non, pour les déchets électriques, comme métal. 500 mètres de profondeur. Les déchets, ça chauffe les roches. C'est pas beaucoup.
Les déchets sont chauds là.
Ouais, parce que c'est exothermique.
Oui, parce que ça
La
continue
radioactivité.
ça continue à et ça s'arrête jamais.
Peut-être. Avant, Pizza, tu fais quoi?
Moi, c'est une petite poche qui me tient une goutte.
C'est bon.
Puis, je suis ingénieur de développement système.
Non, pour moi, je suis Charles. C'est tes collègues d'Ivrogne?
Non, pas encore. Gérard, oui, il est espagnol, est collègue d'ici de Paris, et Phil, il est collègue du labo. Il est doctorant d'ici et il travaille là à Bosch.
C'est allemand? C'est celui qui bosse à...
Ah non, mais vous êtes collègue, il est aussi catalan.
Ah ouais?
Du Nord, catalan du Nord. C'est serré. Ça peut être plus.
Ça va?
Oui, ça va. Pas trop le monde.
Timing, c'est bon?
46, 47. Hier, on a fait 48 avec le stress. C'est ça que m'a dit Sophie.
Tu parles plus vite?
Ah oui? C'est sûr.
J'ai pensé que c'était le contraire.
Non. Si tu connais bien ton texte et que tu
En fait,
si tu maîtrises ta présentation, tu vas aller plus vite.
D'accord.
Tu vas commencer plus vite.
J'ai pas rédigé comme.
Non, mais tu vas commencer plus vite. C'est ça qui va sortir vite. Et voilà. Il y a tout ça de bouteille d'eau pour tout ça dans le tête?
Oui, mais il y a un élément.
Je sais pas. Je vais te dire. J'ai entendu Claude dire que je ne connais pas. Ça va?
Oui,
sinon, t'es serein?
oui. J'étais moins serein à cause de toute la logistique que de la.
Voilà! Pas trop fort. Oui, c'est toi qui as fait ça, la logistique?
Oui. Non, ça à ma mère, la cuisine de ma mère. Il y a 8 ou 10 personnes qui font des événements.
C'est normal. Enfin, c'est normal qu'il y ait des gens pour.
Il y a la moitié du groupe, par exemple, il va filmer, et il y a autre personne qui va faire le streaming.
Si ça peut être oui, tu rigoles, ça te détend. Ah non, l'alcool m'amène dans des domaines inimaginables.
Voilà, ça sera bon.
Il y a ma femme qui vient, on a des papiers, elle cherche un revenu. D'accord. J'espère que si les questions finissent pas à 5 heures,
J'espère qu'il y aura pas de personnes qui vont mettre des questions.
Ouais. C'est aussi des réponses. C'est bavard aussi.
Bavard, ça veut dire que j'ai pas envie de dire.
C'est pas grave. Donc là, il y a qui tes rapporteurs, c'est qui tes dommages coréens et
non.
tes grands?
Il y a Boyle, et puis comme je pourrais avec Pedro Alvarez Costa,
examinateur. Donc c'est eux qui poseront, c'est ces quatre-là qui vont poser la question.
Oui. Et Pedro, il va être.
Il va être très content ou...
Non, très content.
C'est bien. Il est espagnol.
Non. Il y a deux Portugais, un Belge, flamand, et Il est mon directeur de thèse, et il est chez nous.
C'est son chef. Il est chinois en France depuis 30 ans, mais il parle français comme je comprends, j'ai du mal à le comprendre.
Tu peux faire bien, Paco.
Hein?
Paco, tu peux faire son accent.
Ça stream, là?
Pourquoi?
Ça stream. Ah, oui, tout. Excellent.
Puis tu le fais vraiment pour les slides.
Non, ça parle pas le slide. Ça va afficher ça, donc ça va rien se voir. Mais au moins, ça va se voir la tête.
Donc tu stream
Avec la mère de webcam d'ici.
Ah, d'accord. Tu stream ça.
Oui,
Tu stream le
oui.
ton.
Oui, ça c'est un streaming.
Et ça, c'est diffusé maintenant sur YouTube?
Oui.
Mais qui c'est qui regarde tes collègues?
Oui.
Mais c'est privé ou c'est public? C'est public. What the fuck, quoi.
J'ai déjà envoyé l'invitation à.
C'est moderne comme mec, quoi. Mais en gros, donc ils vont filmer les slides.
Ah, et même, il y a un des amis qui va me mettre un bracelet pour voir combien de pulsations par minute il va avoir pendant toute la. On va s'amuser à monitoriser.
Il faut qu'il le mette maintenant.
Si je vais parler de monitoring, il ne va pas.
Mais tu l'as ton bracelet ou il va te l'amener?
Il va me l'amener, il est dans le. Il est pour moi. Mais hier, on a fait des tests et ça marche super bien.
Il va te montrer que tu montes à 300.
Non, normalement, j'ai 49, 48.
Question, monsieur Alves Costa.
49, 48.
49, 48, c'est mon bit per minute. Normal.
Au repos?
Au repos.
C'est
pas, hein?
c'est rien, hein?
Oui.
C'est un
Et puis-
ça, c'est pour un profil professionnel.
Un peu moins encore, mais c'est déjà très bas.
Moi, je serais maintenant à 160.
Ah, no seas tímido. Agustín, tú te iba a decir de ponerte aquí para controlar el ordenador que está haciendo el streaming.
Mais on ne peut pas faire de blagues ici.
Attention à ce que tu dis parce que c'est un streaming du tout. Paco, il est en cause. Après, on a les mêmes directeurs de thèse.
Ouais. Je dis rien, t'inquiète.
J'espère que ça va fonctionner. On a pour 8 heures de streaming.
Ouais.
Ah,
Mais qu'est-ce que je fais?
Tu t'inscris sur YouTube, salut.
C'est sur Google+.
Ouais.
Et donc, il y a Hangouts en direct.
Ouais.
Et tu peux faire une transmission qui va se publier en même temps dans ton profil réseau social et dans ton compte YouTube. C'est génial. Et après, tu as ton vidéo qui est sauvegardée à YouTube. Et je vais te montrer, mais la qualité, c'est pas énorme. C'est à cause de ça. Et c'est pas que la webcam, c'est la merde de connexion Internet de l'école de Ponts qui est la chose qui bloque. Parce que c'est la.
Pour streamer, il faut quand même envoyer ça.
J'ai 65 mégas par seconde et avec ça, c'est pas top.
Par contre, pour les vidéos, je peux faire deux qualités. Vidéo. Mais si je fais un vidéo, je pense que ce n'est pas suffisant aussi pour les questions.
Non, je pense que la chose la plus importante, c'est la soutenance. Ouais. Pour ça. Après, les questions, tu peux le faire dans la qualité plus basse.
Et si vous ne pouvez pas le faire, c'est ta place.
Ouais.
Pas...
Je pense que la chose la plus importante, c'est la soutenance.
Donc, je fais ça en qualité haute.
Juste une chose, attention, c'est comme à la conférence où on était, il y a 2 écrans.
Oui.
Donc,
normalement, je vais être là et je vais signaler surtout là. Donc, je vais demander aux gens de se mettre au centre. Parce que sinon.
Il n'y a pas d'écran.
Ouais. On doit se mettre au centre ou là.
Ou si tu es ici, montre sur celui-là. Je ne sais pas. Mais fais attention à bien montrer où tu montres.
Bonjour.
Mais pas que si tu montes là, je filme ça.
C'est un peu dommage.
Si tu arrives à faire ça, oui. Si tu n'y arrives pas,
Oui, elle est cool. C'est pas assez sombre.
Ça marche pas? Bon, on laisse comme ça. Même si je parle ici, si ça se voit ici, c'est bon.
Ok.
Parce que je ne vais pas aller plus loin des...
D'accord.
Donc, je passe aux toilettes.
Qua per il computer controllare.
Kim Young.
Aquí para los hacemos aquí porque yo las preguntas que yo las preguntas que hacemos aquí todo el rato, ¿no?
No me la hay.
Ah, bueno.
Since when can I commence? Since
Bueno, pero el que no esté ahora conectado ahora mismo, luego lo voy a quitar. Luego voy a quitarlo y voy a poner el bueno. O sea que no os preocupéis, si no había nadie conectado ahora, da igual lo que hayáis dicho.
Tout le monde peut.
Oui, c'est public. Oui, c'est public, mais personne... Déjame la pulserita para medir esto. Es que no tengo boli. ¿Sí? Toma. ¿Esta parte va para abajo?
Non, je dois compter l'ordinateur. Et c'est technique. Around. We understand it.
Le van a...
Vamos así.
El wifi no funciona para los invitados. No, pero que no funciona. Sí, pero reconecta, porque tú tienes cuenta de todo.
Fait que si oui,
Si queréis poner una, pues puedo hacer la fotografía. ¿Cuántas naranjas podéis?
Ma questo comunque è una cosa che penso che
lift to put the flaker. During the Sure, you come in late, last some music.
No, mais
I don't know if it, because I don't know if there's a maximum. Let's go directly to the center. Apparently the jury didn't check the Facebook properly.
Bonjour à tous. On va débuter ce jeudi où je préside, où j'ai le plaisir de présider. Mon nom c'est Antoine Schneidel, professeur à l'Université de Viva. Nous avons aujourd'hui la soutenance pour le docteur à l'Université de Paris-Est, spécialité géotechnique par M. Francisco Lamas-Lopez, avec la contribution d'études in situ et en laboratoire sur le comportement dynamique des matériaux constitutifs des plateformes ferroviaires classiques dans le contexte d'augmentation du trafic. Puisque, comme c'est toujours la bonne habitude française, on a été bien reçus, on a pris un petit peu de retard, mais on est encore dans les 15 minutes de tolérance académique. Je vais donner tout de suite la parole au candidat que je voudrais féliciter et dirais que tout se passe bien dans votre présentation et dans votre discussion avec les membres du jury. Et après, je ferai la présentation à tous les membres du jury. Allez-y, vous avez 47 minutes de faire votre présentation.
Okay, merci beaucoup, Monsieur le Président. I will do this defense in English, and thank you very much, Mr. Chairman. Thank you very much, members of the jury, ladies and gentlemen attending this defense. Today, I'm presenting my PhD study entitled Field and Laboratory Investigation on the Dynamic Behavior of Conventional Railway Tracked Materials in the Context of a Traffic Upgrade. This work has been supervised by Professor Julian P. and this has been performed in cooperation between Ecole Ponts and SNCF. Well, this presentation has 6 different parts. I will start with an introduction of the industrial context of this study, and then I will pass to explain the 2 main parts of this study, the in situ investigation and the laboratory investigation. The in situ investigation will be explained by an analytical model. And then, finally, I will do a comparison between the in situ experimentation and the laboratory experimentation. For finally, give my conclusions and present the further research for this study. Then, starting with the introduction. Mainly, nowadays, there are about 94% of conventional tracks in the French railway network that are not new lines. Then SNCF has planned to upgrade the conventional line by increasing both axle weight and train speed. Then, which is the difference between a new track and a conventional track? Nowadays, we are setting the ballast over the subbrake with 2 different layers that are doing a transition through the subbrake, that are the sub-ballast and the capping layer. But before, the ballast was set directly over the subbrake. And then, with time, a high dry density with high volumetric fraction of ballast grains and low permeability layer is formed. This layer is the interlayer, which has also a transition layer through the subbrake that we can see here. This layer is heterogeneous and depends on the site. And the finds that are the matrix of this layer came from interpenetration from the subbrake layer. Then, but what is the effect of the train speed on the behavior of tracked materials? Some unknowns remain when we are dealing with that, and to calculate the ability of the tracked materials to accommodate an increase of the speed and the effect of a speed increase on conventional tracked materials. Before, in Sweden, Mashus and Kenya studied a case in which there were problems with cohesive soils and the shear wave velocity was very low. And then they stated that from a cutoff speed, there's an amplification of the deflection on surface till a critical speed that is related to the surface wave velocity on the site. Then we can distinguish two domains, a quasi-static domain and a dynamic domain, in which we have loading and response amplifications. Then nowadays, SNCF take into account the train speed effect in an empiric way. And that's why we are doing this study, because we have different objectives. Industrial objectives, for example, to integrate the effect of train speed in maintenance needs and renewal operations, establish an experimental protocol to assess the train speed impact and evaluate the resiveness depending on different trains typology. Then the scientific ones are to explain how both loading and response of travel materials are amplified when train speed is upgraded. Then investigate also the train speed and the axle load effect as short and long-term effect. Also, we want to determine the effect of loading shape on travel materials and assess the evolution of the dynamic parameters depending on the loading history. Also, we want to define appropriate parameters for field and laboratory comparison. Then, the methodology is the following one. Firstly, I will present the in situ experimentation. This in situ experimentation is explained by analytical modeling, and then I will use both results to implement a laboratory experimentation. Finally, I will perform the comparison between both. Then, moving to the in situ experimentation, I will explain the different criteria that I have used to select this site. We have about 32,000 kilometers of line in France and about 29,000 are conventional lines. These lines, the maximum train speeds is about 220 kilometers per hour. And the maximum load is 225 kilometers per hour. Then, in this case, we will have a huge range of different trains running at different speeds. Then only 17 sections has these characteristics. But we need also a recently renewed track to avoid unwanted dynamic interaction between wheel and rail, and that only 3 sections correspond to these characteristics in Angoulême, in Strasbourg, and also in Vierzon. We choose Vierzon because there were a good alignment and good accessibility. Then this is the Vierzon site. But prior to install the sensor on the site, we have performed a different site investigation. Different tests have been performed on the site. For example, 4 MISWB profile, 12 gyroscopic tests, 30 panda, and 24 lightweight deflectometer. Well, with the gyroscopic test, we have found 4 different materials in the track bed. Firstly, the ballast, then an interlayer of about 40 centimeters, a 20 centimeter transition layer, and then the subgrade. That is a seal design. Then I use the thicknesses to interpret and analyze the different panda test data, and an analytical, stochastic statistical analysis of this data has been performed without formulation to analyze the different modulus of different layers. This modulus has been compared to the modulus, global modulus or global stiffness obtained by the lightweight deflectometer. Then we can see here that the modulus in blue from the lightweight deflectometer are coherent to the modulus obtained with the empirical formulation from panda test of about 100 megapascal in surface. Then once we have the different thicknesses and once we have the different nature of different layers, we are able to install the sensor on the site. Then 4 different installation depths has been considered. Then on surface, a slipper, in a winter layer, 1 meter depth, in depth, transition layer 1.2 and subgrade 2.3 meters. Then about 42 sensors has been installed on the site, mainly on track 1. 33 of them. But 9 of them have been installed on track 2 to evaluate the repeatability and the lateral propagation. We have 3 zones. The first one is a zone of repeatability in track 1 with accelerometers on interlayer. The second one is a zone with different stress sensors at different depths. And the third one is a zone with accelerometers and GFOs at 3 different depths: interlayer, transition layer, and so on. Also, we have a reference point with a strain gauge glued to the right to analyze the load on rail. That is the reference on the site. Then, for each train running on the site, a trigger is start to record all the data for all the sensors, from all the sensors. 1,200 Hz of sampling frequency and during 45 seconds. We have here an example of axle load during an intercity train at 200 kilometers per hour, the stress sensor at the interlayer for the same train, and an acceleration signal during the passage of this train. When we are doing a power spectrum density of this signal, we obtain that different energies are excited and different amplitudes are obtaining this power spectrum density depending on the different wavelengths present in the system. For example, the biggest one influences more the lowest frequency, as for example, the axle distance or the bogie distance or even the coach length. When down integrating this signal with proper corrections and proper filters, we can obtain the displacement at different depths, the depth of the installation of the accelerometer. For each train passing on this side, the amplitudes are calculated from the peak under the axle load to the stabilizing zone in the middle of each carriage. Then an average is calculated for all the axles of the same weight load, locomotive or coaches. Then, if we are doing a cumulative PhD of this kind of signal, we can see that there's a decrease of the total energy in depth, and also that all the frequencies excited by wavelengths lower than the axle distance induce more than 99% of the displacement energy. Then, when we are doing verification of this kind of measurements, for example, on a sleeper, compared to LVDT measurements that are direct measurements of the deflection at the sleeper, we can see that there's a realistic agreement between the different deflections at 100 Hz of filter with the deflection amplitude obtained by the LVDT for different axle loads. And there are also a great repeatability using different sensors at the same place. Also for embedded accelerometers or gyrophones, when integrating once or integrating twice these accelerometers or gyrophones. Then we have a good repeatability for both axle load and same position. Then going directly to the calculation of the strain, in order to virtually simulate that all the sensors are installed in the same borehole, I have to do a translation of the signal depending on the train speed. And then using accelerometers at different depths, we are able to calculate, to estimate the vertical strain of each layer. That, for example, is shown here, and the amplitudes are calculated in the same way as the deflections before. We have the average of the locomotive and the average of the coaches. Then, well, I will explain here the train that was used during this study. Firstly, we have used a test train. Why a test train? Because with a test train, we will avoid the unwanted dynamic interaction between rail and wheel. Then also, why an intercity train? Because the intercity train is able to cover a huge range of train speeds from 20 to 200 kilometers per hour, and we have different axle loads in the same train. Then we have done 6 different speeds from 60 to 200 in the regular direction on track 1 airways. Sorry. Then, but also we have analyzed the commercial trains that have been registered during 5 months, and about more than 1,800 trains have been recorded that are more or less 43% of all the trains running on the site. Each train had between 7 and 60 coaches. That is a good number to reduce the variability of the average calculated. Then, with 3 different variables will be analyzed in the following slides, that are the amplitude of the stress, the amplitude of the deflections, and the amplitude of the vertical strain. Firstly, the stress amplitude. We have an amplification that is is larger in the shallower layers as the interlayer, that goes from 10 to 15 kilopascal for the locomotive, for the test train, and that is more flat for deeper layers as the subgrade. The same, there's also a difference between different axle loads as the locomotive and the coach. We can see here that there's a good agreement with the with the commercial trains for the interlayer here and the subgrade here. There's a low dispersion of about 7% around the average value, and there's a quasi-linear amplification in the range of the considered speeds, and a higher absolute values are found in shallower layers. It means that there's a linear influence of the axle load. Regarding the deflection amplitude, we have a larger increase amplification of this deflection amplitude in shallower layers in the interlayer compared to the subgrade, and we can see with the commercial trains that there's also a low dispersion around the average. Most of the deflection amplitude is decreased during the interlayer, the 30 centimeters of the interlayer, as we can see in this comparison. The same analysis is performed for the strain amplitude. A larger increase amplification of the strain amplitudes is found in the shallower layers as interlayer, and this is more stable, more flat for subgrade measurements regarding locomotive and coach load axles. This amplitude goes from 0.03% to 0.07%. Then the same evolution is found with all the commercial trains that has passed on the Vierson site. Then, when we have the strain and the stress signal, I'm able to calculate the hysteresis loops for different axle loads, for different trains that are running at different speeds, and also for different depths. Then here I show an example of hysteresis loops of a locomotive at 60 kilometers per hour, and I show also the method in order to calculate the resilient modulus with the ratio between the stress amplitude and the vertical strain amplitude, and also the method to calculate the damping ratio, that is the other main dynamic parameter, with the elastic equivalent energy given to the material and the energy dissipated by the material during the loading and unloading cycle. Then, when regarding the modulus evolution at different layers with speed, we can see that there's a larger decrease in shallow layers at the interlayer compared to the subgrade evolution of the modulus. And regarding the damping ratio, we have a light increase of the damping ratio in shallower layers. That is not the case in the subgrade. We have compared before that the the results with the commercial trains are the same, I will only show the resilient modulus evolution with all the commercial trains. That is the same as I showed before with the test train pattern. Then all these results could be explained using an analytical model of the stress transmission and the deflection propagation in the track. Then firstly, I will explain how different trains running at different speeds could be compared. Then, for example, here we have two different trains at 60 and 200 kilometers per hour, and we are able to convert from time domain to distant domain, that's some cycle, we multiply time by train speed, and then if we extract different axle loads, we are able to analyze, to assist the longitudinal propagation of different variables depending on the axle load. And also, we are able to perform a boogie extraction. This boogie extraction is shown for two different boogies of coaches at different layers, interlayer and subrate, and for different speeds. We can see that there's a different shape of the stress that is submitted at different depths, depending on the depth and also for the speed, because there's an amplification with the speed, so it's different in the different layers. Then this effect could be assessed using different elastic stress distribution models that exist right now. For example, the Bushing elastic model, using, for example, a point load on the track, using an uniform load model from, for example, a slipper, considering a monolayer, and, for example, a load spread model, considering a multi-layer soil. In this case, with a multi-layer soil, the spread load angle is calculated from the ratio of the modulus of adjacent layers. Is in this way that these spread angles evolve. And when calculating the stress peaks just under the axle load, we obtain that this last model of a load spread model with the data from the zone is more realistic according to the measurements. But this is more realistic just under the axle load, but the longitudinal propagation is not correct. Then I propose a modified spread model that have also a normal distribution of the load at each the interface of each layer, and the diffusion angles are also calculated as before for the Bushing load spread model. Then, when performing the calculation using this model, we obtain that it's more realistic, the results according to the amplitudes at different layers, and also the shape here at the interlayer, and the shape that is not M shape at the subgrade. The equation that defines this model has two terms. The first one is the effect of the axle load and the dynamic amplification with the speed, and the second one is the normal repartition in longitudinal direction of the stresses. Then I pass to explain the deflection propagation in different track beds, in different materials of a track bed. This deflection propagation has three simple mechanisms. For example, we can see here the deflection propagation at the interlayer of a coach, and the deflection propagation at the transition layer of a coach. The amplitudes are calculated as I showed before, and the three mechanisms are the amplification of deflections with the speed at every layer. The second one is the decrease of deflections in depth, and the third one is the longitudinal propagation at each depth, and also the amplitude at the origin, that is the elastic amplitude under the load. Then the deflection amplification with the speed, from several studies, one of them carried by Professor Alves Costa, I took one of the profiles presented that is similar to the ozone profile, and I fit my results of amplification of different layers with the equation, and we obtain an analytical model using one one parameter that is the ratio between the train speed and the shear wave velocity, obtaining that in all the layers the amplification is close to the others, is approximately the same. The second mechanism is the deflection attenuation in depth. If we consider a homogeneous media with only one material, we can obtain, for example, the median. The average line is the black line that is considered in this study. But in the real case, we can see that there's the main decreasing appears through the interlayer to the transition layer of the deflection amplitude. Then, finally, the homogeneous layer is taken into account from a formulation shown by Hours in 1994, which used a damping parameter index. And the third mechanism is the longitudinal deflection propagation that is based on a Winkler beam model, simplified, and the amplitude at the origin is taken into account from the axle load and the global stiffness. Then, using this model proposed by me, we are able to have a more coherent approximation to the real measurement, and as we can see here, the comparison between measurements and vibration models for different axle loads at different depths at different speeds. That may be very interesting for the railway industry. Then, with all these results, I have performed a laboratory experimentation that is based on the previous results. Then, for this laboratory investigation, I have mixed in laboratory a soil, an interlayer soil, because of the non-possibility to obtain real ITL samples in tracks, in conventional tracks, and the interlayer of Senisia that is shown in the thesis of Trim in 2011 was used as reference. Then 13 different materials from ballast to clay were used in this interlayer soil and compacted at 4%, that is the optimum moisture content of this material. Here we can see the grain size distribution of all materials from the ballast to the clay. And here we can see the different aspects and different grain size from ballast to clay. Then, when this material was mixed, we can see that there's a good agreement with the grain size distribution of the reference soil and also the same plasticity, not only between the inter-ITL laboratory layer and the layer in Senisia, also with the soil from Vierzon. But not only that, we have a good agreement with the shear strength parameter of ITL laboratory soil and the reference soil, and there's a good agreement between cohesion and internal friction. Then, with this material, different triaxial tests were performed. The interlayer soil was tested in these large size triaxial cells with samples of 300 millimeters of diameter and 600 millimeters of height. All the samples were compacted at 2 megagrams per cubic meter and with a moisture content of 4% in this steel mold. From this steel mold, the sample was set over the apparatus and protected with a latex membrane. Then all the samples were carried at consolidation pressure constant of 30 kPa. The dry density was always the same, as I said before, of 2 megagrams per cubic meter for all the samples. And the objective of this program is to evaluate the moisture content effect, the loading amplitude effect, and the loading shape effect on the development of permanent deformation and large number of cycles, and the evolution of dynamic parameters as the resilient modulus or damping ratio when we are performing variation in the loading history. Then I will show that here in the next slide, the different test procedure. There is one procedure that is the long-term test that has 5 different loading stages from 10 kPa to 30 kPa according to the results obtained in situ, with 90,000 cycles per loading stage. And the objective of this test is to analyze the evolution of permanent deformation. The second procedure is a short-term test that has only 50 cycles per loading stage that go from 10 to 50, from 10 to 100, and from 10 to 200. And the objective is to analyze the dynamic parameters evolution. Then I will explain the different shapes that has been performed on the samples that are the M shape and sine shape for materials with different moisture content. 4% moisture content, optimum moisture content, and 10% saturated conditions. Then, regarding the M-shaped loading, we have here 3 different cycles, and for the sine-shaped loading, we have here also 3 different cycles, from 10 to 30 kPa of amplitude. All the tests were governed by loading amplitude, the loading amplitude. Then, if we perform a power spectral density on these 3 different cycles, we obtain that 3 different frequencies are excited in the M-shaped signal, while only one frequency is excited for the sine-shaped signal. But always the amplitudes in the sine-shaped signal are larger than the amplitudes in lower frequencies compared to the M-shaped loading, as I will explain later. Then, for the first procedure, the permanent strain were calculated during all the test procedure. But how to avoid the history effect on the sample? For example, if we take only 2 loading stages, we can take the second loading stage previous to a previous one, and we translate that to the origin. And then, using a formulation given by Gigel in 2001, we are able on post-grain soils to adaptate how the permanent deformation evolution could be if no previous loading has load on the sample. And when we perform a comparison between the measured one and the estimated ones, we can see that there's a current agreement between both. Then the total deformation amplitude is taken into account as the amplitude at the 90,000 cycles for each one of the loading amplitudes. Then we can see, for example, the moisture content impact on this soil that shows that when the soil is saturated, for example, with bad drainage conditions in real conditions, we obtain more than 100 times the deformation, the permanent deformation on the sample, with the same initial condition, excepting the saturation condition. But not only that, if we normalize for different moisture content, for example, for a saturated condition, we can see that more than 80% of the total amplitude is developed for the first 20,000 cycles if the soil is saturated. That's not the case if the soil is not saturated and the permanent deformation are taking more slowly. Then, when we are performing in the stabilized zone after some 1,000 cycles of loading, where low plastic deformation are performing after each cycle, we can take, for example, 10 cycles, and we can see that in the loading, for the same shape, we obtain that the amount of energy is the same, even if we not take into account the moisture content. But in the response, we can see that this is very different. The moisture content is very important because the saturated ones have a response much energetic compared to the samples at the optimum Morpher point. Then we can say that sinus-shaped signals, in this case, with the sinus that I have applied to the samples, this signal induces more energy, measuring the power spectrum density, to the system. Therefore, the response is larger, mainly for saturated soils. Then, if we calculate the cumulative PhD depending on the loading amplitude, we can see that there's a linear relationship for all the test conditions, but this is not the case when we are analyzing the same thing with the loading, with the vertical axial strain regarding with the cumulative PhD of the axial strain. This depends on the Morpher content and not on the loading shape. We are always on the same line. Then, as we are adding low permanent deformations to the sample in this range of cycles, we can see that the relationship between the load here, and the response is related to the elastic behavior of the soil. That depends on the loading shape and also on the Morpher content of the sample. Then we are also able to relate the loading amplitude to the maximum deformation obtained for each loading amplitude at the end of the 90,000 cycles. And we can see that there's also an influence of the loading shape. Because the side load was more energetic, we obtained larger deformations. But if we compare that with the energetic response of this number of cycles, we obtain that all of the energies developed then in the axial strain are in the same line depending on the initial state conditions, for example, the Ewing conditions. And we are able to say that a larger cumulative PhD content in the response implies higher deformation rates or aggressiveness to a material. Then, also when discussing about the loading history impact on dynamic parameters, we can see that there's an influence on the hysteresis loops. And it seems that the second modulus is decreasing with the loading amplitude, and also the surface of the hysteresis loops is evolving. Then we can see here that the evolution for the second test procedure concerning the resilient modulus is parallel for different Morpher content, being always larger when the soil is at the optimum Morpher content, but always when a new higher load impact on the material, we obtain a decrease of the resilient modulus, and then this decrease is stabilized in time. That means, for example, here with 100 and here with 200 kilopascal of amplitude. But concerning the damping ratio, we can see that the damping ratio is more or less the same for both Morpher content in condition, but when the soil is saturated, there's a larger amplification of the damping ratio in the first cycles, and then this is attenuated in time and goes to the previous level. Then, using all these results, I will perform a comparison between in situ and laboratory. Then, because as we can see from the response of a material, we are able to assess the aggressivity of a load on the material. Then let's analyze with in situ results, in situ measurements, what happens with different traits. Then, as I said before, the relationship between load and strain is related to the hydric conditions, and also mainly related to the loading shape. And let's see if the different deformation response in the response signals are obtained for different trains. Then two different trains with different spatial configuration of the axle loads are taken into account. The first one is a TER, and the second one is a TGV. Both of them have the same axle load. That is about 15 megagrams per axle. And I have taken 8 axles for each train that I suppose that are equivalent loadings. Then, for example, let's assess if the loading is the equivalent for both. Then I have taken the same number position of the sign signal for both trains for the 8 axles, and then the power spectrum density is analyzed, and we can see that different frequencies are excited because different wavelengths are present in the different trains. Then, when performing the cumulative PhD of both, we obtain that more or less the same energy is developed by the two of them with about 7% of difference. But this is not the case regarding the response. In this case, I'm analyzing the displacement because it's related to the strain, and I take two signals of the two trains at the same level as the loading in the interlayer. We can see in the power spectrum density that different frequencies are excited during this response, but there's a larger difference in the cumulative PhD of this response. That's important. Then, if we analyze the responses at different depths and for the different trains in the same range of the speeds, we can see that always the TGV coaches have developed larger response on the accelerometers. Then that's very good, but let's analyze if we are able to do the same on surface, because it could be interesting for SNCF to measure that on surface, the response of the energy on surface. Put an accelerometer on a sleeper, that's very easy. Then let's assess if I was right and the loading is equivalent for both trains. Then, using the strain gauge that was glued to the right, I took the signal for both trains, and well, the frequency excited for each train is different. Then, but that's important, the total energy is the same for all the 8 axles in both trains. That's the point. Then, analyzing the total energy that is developed in the same accelerometer for different trains, we obtain the same results as for the embedded accelerometers. Then we have that always the TGV configuration of the coach axles has developed higher responses. And that means that TGV could be more aggressive to this solve. Then let's move to the conclusions and the further research of this thesis. Now, firstly, I have found that there's a dynamic amplification that is related to the speed and the load upgrade. That means that there's amplification of both loading and responses that are quasi-linear in the test conditions. But also, it means for the industry that upgrading the speed or the axle load will result in higher loads and larger responses also. Secondly, I can say that the load distribution could impact the track response, and different axle configurations could lead to different energy contents in the material response. This suggests that different aggressiveness levels to the track bed, but the saturated state is a critical situation. But for the industry, that's also important because the aggressiveness of different trains can be evaluated through on-surface monitoring, using, for example, accelerometers, honestly. Then, thirdly, dynamic elastic parameters. The evolution of the dynamic elastic parameters depends on the loading history. And when new higher loads impact a layer, a rapid modulus decrease and damping rating increase happens, and especially at the saturated state. This phenomenon is attenuated in time. And for the industry, that is also important, because the deflections may increase and the axle load just after a speed or load increase. And finally, last but not least, a simple track analytical modeling of the dynamic behavior has been presented of the stress propagation and deflection propagation. Then, track dynamic behavior is governed by 6 parameters in the case of the deflection propagation and only 4 parameters in the case of the stress propagation. For the industry, that's also important because the track performance in the case of a change in the load of track or track bed configuration could be easily assessed. Then the further research topics or perspective that I could present here are to study the influence of ballast grace volumetric fraction influence on ITL soils, the use of continuous passive MIS-BB on railway tracks to assist the continuous behavior of the track, on the continuous evolution of the dynamic parameters, as receding modulus or even the damping ratio, and further analysis on the transfer function between different layers during train passage. Then, also for SNCF, there's some industrial perspective as update the SNCF standards. The need to update this standard concerning the track bed design or the speed upgrade impact, not only on the track, but also on the track bed, and developing a track wireless continuous monitoring on the railway network. Then that's all. Thank you very much.
Thank you very much to be in time. So you can breathe a little now, and I will do the presentation of members of the jury. So I will start with the reporters. And I ask the members to stand up when I call you. It's more easy for the participants to know each member. So I will start with Professor Herman from Professor Pierre from the University of Pascal. Dr. Pedro Alves Costa from the University of Porto. Professor Jean-François Samblar from IFSA. Dr. Jean-Claude Dupin from Ecole Ponts Engineer Nicolas Calon from SNCF, Physical Engineering. Dr. Sofia Costa Raguiar from SNCF Research and Development. Dr. Chaussées from SNCF Physical Engineering. Dr. Anmin Feng from Ecole Ponts Dr. Jean Perrou from Ecole Ponts Mr. Alain Moyer from SNCF Physical Engineering. And last but not least, Professor Julian Cui, that I also congratulate you because you are the director of this thesis, and it's very important to achieve this stage. It's really a very interesting work in cooperation of the Ecole with the SNCF. I think that this is really strategic, I will say, for a country where this vision, because this fits 100% what is nowadays the horizon 2025, is to put what research and development to innovation for industry. So this is I learned is fully in this objective. So congratulations for the supervisor and for SNCF to have this mission. So now we will start the discussion, and I ask the Professor Catherine to start. Thank you very much.
Well, Francisco, first of all, I know you still have to undergo this questioning session, but I would like already to congratulate you for the very nice, clear presentation. You demonstrate that clearly explain technical issues, but of course also for the work delivered. I enjoyed reading your thesis. I also enjoyed listening to you as previous occasions at conferences. I think this is an important work. A lot of experimental work has been done, both in situ and in the laboratory. And we all know that this, first of all, takes time, takes a lot of consideration, takes analysis, a great amount of work, both for SNCF, but I think also for the whole engineering and scientific community. But I have been asked also to ask you a couple of questions, and I would like to start with some, let's say, more general questions regarding, well, we started off mentioning the critical waste. I know the measures we have been doing, we are at close to 40% of the critical waste. But I would like to ask you some questions about railways and critical waste. Since you mentioned on, can I refer to pages in the thesis? You say the surface waves, railways, contains and transports more energy as compared to the compression and shear waves. And then you say, even though they are slower than the other two others. And I was asking myself, why do you write even though? I mean, does it mean that if the wave is slower, that you would automatically expect that the displacement would be higher? It reads as if you are surprised by that.
Yeah. In fact, in the case that I studied in the literature, all the cases were concerning clay sites with very low shear wave velocity. And in these cases, it was this case that was explained in the literature, and it was because of that I was writing that in the literature review. But it depends on the site. I agree with you that it depends on the site, on the material. In fact,
the railway velocity is expected to be lower than the shear velocity, no problem with that. So the amplitude will be higher.
yeah, the amplitude will be higher, and that's the important thing to evaluate how the load, the response will be amplified depending on the generation of railway surface waves, because these surface waves will depend on the different configuration of the track. It depends on the rate. It is also concerned by the track conditions, and it's because of that we have to take into account all in order to say which is the critical speed of a site. Yeah.
But regarding still the railways, you also say, look, the shear component amplitude is predominant in railways. And later on, I read when you discuss the MASW test, and that's on page 87. You say that for the MASW test, you use shear wave geophones. But what exactly do you mean with the shear wave geophones?
The shear wave geophones are geophones that are able to receive the shear waves instead of the compressional waves. It were used to to perform the MAS double B tests.
That means on the screen on page 87, the configuration.
Yeah.
That refers already to the CPU testing that we have done. Did your phones measure the horizontal velocity of
The horizontal.
Then regarding that little noise speed,
Yeah.
there are some contradictory sentences in the first chapter. When you first cite Professor Philo from Labour, and you say the critical speed of a track is reached when a train runs at the railway velocity of the ground.
Well,
Then you correct yourself, and 10 lines further you say, oh no, the critical speed of the track is fully dominated by the properties of wave propagation in the embankment and
yeah, I was wrong in the first sentence. I agree with you because the surface wave velocity will depend on the wall track configuration. Yeah.
And then we have the author of that paper with us, but we then refer to the work of Chaussées. And you give us 3 figures, and in the text you say, I'm talking about figure 134. It's about layer cells. And it's also about the discussion of critical wave velocities. And you say in the text, referring to those figures, however, when the ground is layered, the critical speed should be somewhere between railway and shear wave speed of the upper layer. But isn't that contradicted by the third example given in the literature, and also by the third graph in page number 14?
I agree because it depends if the subrate characteristics, for example, the shear wave velocity in the subrate is much lower, will influence it more the development of the subrate wave velocity. If we compare the influence of the subrate with the traveler materials. It is not always the case, it depends.
Then I have a question about the nice picture that yourself.
Yes.
You measure or you report the measurement of strains in the soil. We know that's not an easy undertaking. And what you've done or what you report is that you have taken measurements from accelerometers that have been placed in boreholes at some distance from each other. And that distance could be 20 centimeters or it could be 70 centimeters. And then you integrate that acceleration twice located in this place. And then we come to page 134. And you give an expression for a strain estimate as being the difference of the displacement measured divided by the distance between those 2 sensors. That's how I interpret the measurement. And you illustrate this with a figure on the next page, and following pages you report on strain and stress, and from these strain stress measurements, you then derive moduli and also the period of that. Now my question is, can you comment on the use of equation 242? So how accurate is that strain estimate?
We have about 5% of errors in this using this equation in the worst case. The worst case, because I was measuring, I have different boreholes with different accelerometers. Depending on the train speed, I translate the accelerometer to the right position because I know the train speed since the trigger was launched. Then I correct the positions to simulate that all the accelerometers are in the same borehole. This error I have measured that performing different positions, for example, 1 position less, 10 position less, 20 position less, to see how much error is in the vertical amplitude that is the parameter, the variable that is important for me. And I do some suggestions in the manuscript, supposing that the primary wave velocity of the soil is 1,000 meters per second, and supposing the error that I am supposing in the correction is with some different parameters. And when for the subgrade vertical strain, I'm supposing that instead of to be in the same borehole, the maximum error that I obtain is like a displacement of the first accelerometer of about 90 millimeters.
But if I may ask again, you now refer to a correction you have to do because of the fact that your accelerometers may be in different boreholes.
Yes.
But I'm not intending on this error. I mean, strain can be defined in every point of a continuum.
Yes. Yes.
And so it is a continuously varying field.
Yes.
And what you do is you take a microscopic measure
Between
place
so,
is far away, and you take a microscopic, very microscopic measure to be used as an estimate of a local variable. So my question is, did you check that approach? I can imagine later on you show images of models, analytical models that allow you to compute the stress distribution under the crack. And you refer to the Chaussées law. Did you ever implement the equations of Chaussées to obtain strain measures, to obtain displacements, and to check performance?
I checked that once, but I did not include in my thesis, and there were a good agreement between the displacements obtained at different layers and the displacement obtained by, for example, my model. It's true that, for example, in the subgrade estimation, as we are talking about the macroscopic dimension, there's more than 1 meter between the first accelerometer of the transition layer and the accelerometer in the subgrade could be performed. But the subgrade is homogeneous in this thickness, and the evolution of the deflection amplitude through the depth is more flat in this at this depth. Then I think the error it could be lower for this layer because of that, compared to the, for example, if I calculate from the accelerometer the sleeper and the accelerometer and the interlayer, I'm not able to calculate the vertical strain at the ballast because there are a huge decrease between. Yes, I understand. Accurate is, yeah. It's because of that in a zone where there's a huge evolution of the deflection that is the interlayer, the two accelerometers are more close one to another, only 30 centimeters. It was because of that I put these accelerometers in this layer so close in order to calculate that in a more proper way.
But I'm aware that, but we also has stress pressure sensors as well. So you know stress level.
Yes.
So we know that stress levels, estimates of stresses.
Yeah, the stress level compared, for example, with my models.
Compare derived strains from the stress level.
Yes, because but I cannot compare that directly because yeah, the inertia, because when I calculated for example, the resilient modulus in the stereosis groups during a train passage, I'm taking into account also the inertia term, and the values are lower as if I do the same loading in laboratory. Yes.
What inertia do you take?
No, in the real measurement.
The relation between stress and strain.
Yeah, no, in this instance, no, the values are lower.
I have a question on that. The first occasion where you talk about damping is somewhere on page 46. That's the first time that we introduce the material damping ratio GR. And then like you mentioned, look, we have damping ratio 46. And then you come back to it on page 52. But I do not see any D on that page, right?
Yes.
I mean, you come up with some other definitions where I might question what you mean with critical damping in this context. So, Formula 111, you define your damping ratio.
I took that from the article from CAN 2011, and it described the damping ratio using the.
Yeah. Okay, but it's a definition we know from the structural dynamics course for civil systems, but it would be difficult to define the critical damping ratio in this context.
Yeah.
And then you move on much later on page 137 with a more appropriate definition as you use it in Tesis. That's the equation 216. And then you use it. I mean, at the end of the chapter, in page 163, well, you evaluate the constraint or the modulus n as a function of plane speed based on all your measurements. But did you do the same for the damping? I was expecting here to see a graph as well for that.
It was a calculation problem because for every one of the 8,000 trains, well, only 1,800 trains were intercity trains. At the moment, when I calculate all the parameters, for example, amplitude of stress, amplitude of strain, I did not calculate at this time the surface of the loop. And it's because of that I have not present this parameter here. Because at the moment I calculate that on the computer, I have not calculated this parameter, the surface of the dissipated energy in the stress loop. Yeah, I have. Yeah, for sure.
Damping is the most difficult parameter to measure. I mean, if you report on the geophysical tests, you say, look, we can derive shear wave velocities. There are attempts to derive the material damping ratio in a similar manner, but this works.
But it's also because of that I have done the comparison of the commercial trains with the test trains to verify that we obtain the same evolution. And once we have that the test trains have the same evolution as the commercial trains, I said, well, it's the same that I have the same evolution of the modulus and the same evolution of the damping ratio. Because of that, I only showed in the thesis the evolution of the damping ratio regarding the test damping.
Yes, on your slide, I think it was slide number 10, you can show that.
20.
The slide.
Would be.
It's about yes. In the that is about chapter 4. Quite quickly say that you have the left figure shows as a result as a function of time. It has been measured at a constant position. And you quite quickly move on saying, look, let's do a transformation and let's replace time by distance. Can you comment on the circumstances under which that would be allowed to do?
Yeah.
The this was very good. And also, what does the graph mean in that sense?
Then, as all the trains are the same trains, we know very well the geometrical characteristics of these trains. Then we know, for example, the distance between two axles, the distance of one carriage, one wagon, the locomotive. Then I am able to calculate with a very good accuracy the train speed. And from train speed, we have always the same reference position, that is the reference of the strain gauge due to the right. I'm able to multiply the time vector by the train speed. And we obtain the distance of from the sensor. The sensor is always on the same position. The train is passing. I'm only converting time. If I have the whole train, yes. If I know the train speed, and the characteristics of the train.
Suppose that you have a constant moving axle at constant speed already, which is not the case, since you have a constant force plus a dynamic load, which is time dependent. So already there,
yeah,
it becomes different. But also, this track in the zone is a ballast track, so it is not invariant along the track. So it does make a difference whether the wheel is between two sleepers or it's on the sleeper.
But the objective of the ballast is to homogenize the loads at the interlayer. And it's because of that I have verified that at the interlayer, all the stresses that arrive to the interlayer are homogeneous all along the track. And also, the track in the track of materials, for example, interlayer, transition layer, and subbrake, are very homogeneous during the 18 meters of experimentation site. It's because of that I can do that. If we have a lot of heterogeneities in longitudinal distance, I'm not able to do that.
We're confident that we can consider the right figure here as a snapshot, since it's a snapshot at a specific time.
I suppose.
Merci. Francisco, je pense que je vais parler en français, je serai plus à l'aise pour te donner une question en détail. Si tu veux répondre en anglais, il n'y a pas de problème. Je pense que ce sera mieux. D'abord, je voudrais te féliciter parce que j'ai effectivement trouvé que tu as fait un travail important et très dense. Je crois qu'à la fin de ta thèse, tu arrives à des résultats qui sont clairs et qui vont permettre d'appeler des conclusions pratiques ou des solutions pratiques aux gestionnaires des voies ferroviaires, la SNCF ou d'autres compagnies. Donc ça, c'est un point qui est important et à souligner. J'ai noté aussi, comme Gerd, que effectivement, tu as fait un très gros travail expérimental, que ce soit en laboratoire ou in situ. Et il m'a semblé, en tout cas sur les parties que j'étais plus spécialiste, que tu avais porté une attention particulière et beaucoup de soins à tes expérimentations, ce qui donne, je pense, une fois une confiance assez forte dans les données que tu as pu obtenir. Alors, il y a eu, je l'ai noté dans mon rapport, et je reviens un petit peu sur ce qu'a dit Gerd, notamment dans le rapport écrit, il y a quelques points où je pense qu'il manque des précisions, des détails sur certaines définitions de paramètres. Gerd a fait allusion au damping ratio. Il y a d'autres endroits, je crois, où on peut effectivement rajouter des précisions. Donc ça, je te l'ai mis dans le fichier de correction. Tu pourras regarder ça. Je pense que ce sera intégré dans le manuscrit final. Il y avait aussi quelques petites coquilles. J'avais noté notamment page 29 en ce qui concerne la mesure de la résistance de pointe. Où tu donnes page 29 sur l'équation 1,4, donc tu donnes la résistance panda. Donc, en fonction de LGH, énergie potentielle, ici, il faut utiliser l'énergie cinétique. C'est des petites choses comme ça que j'ai notées au fur et à mesure qu'il faudra, je pense, reprendre et corriger dans ton rapport final. Je te remercie aussi pour ta présentation qui était très, très claire et présentée d'une manière un peu différente de ton manuscrit sous un autre angle, ce qui était assez intéressant. Je vais venir maintenant aux différentes questions que j'ai. Les premières vont concerner les reconnaissances des sols in situ. Comme je l'ai mis dans mon rapport, tu l'as présenté au départ un petit peu rapidement, tu as fait une campagne d'essai pour caractériser la voie à partir d'essais de plaques, d'essais pénétrométriques, de différents géophysiques. De là, tu en tires des modules et finalement, on ne sait pas très bien à quoi correspondent ces modules. Quel type de module il s'agit, comment tu les as obtenus et comment tu peux les comparer entre eux. Donc, si tu peux donner ton avis là-dessus.
Donc, je réponds à l'anglais pour que tout le monde. Donc, I have used the endoscopic test to discretize the different panda, the 30 panda that I have performed on the site, on the platform, or on the track, and also on the service paths. Then, from this data, recorded with the panda, each layer has been taken differently, and a statistical analysis of the tip resistance is performed. Then from that, I have used some formulation that has been presented in previous theses, the one from Vinicius Alves Fernandez, and then these modulus are obtained from this empirical formulation. That's are just read.
Une corrélation.
Resistance and modulus. It's not a direct measurement. And then I have compared that with, that is the first time we compare different correlations on trackbed with real measurements of the global stiffness of a track. And I used a small lightweight deflectometer of only 30 centimeters of diameter that will influence mainly the 31st centimeters. That is the global stiffness, the EV2, but mainly for the first layer of the site. But for the lightweight deflectometer, it's about 100 megapascal. But it's very coherent with the estimation that I have done with the formulation.
Le module obtenu par ta relation empirique, c'est un module Young.
Yes.
C'est un module quoi?
Yes. It's not a module de Young, but it's a modulus. It's not EV2 like, for example, the lightweight deflectometer. In this case, it's a global stiffness, but it's the stiffness of the soil depending on the tip resistance in the panda.
Ouais, et le module obtenu par la plaque est un module dynamique.
Yeah, it's dynamic, but it's corrected with another formulation. Is also a correlation with EV2. Then we obtain directly the dynamic modulus, and from this directly obtained dynamic modulus, we correct that with a correlation formula that is presented in the literature to obtain the EV2.
Alors, je pense que tu aurais dû mieux préciser ça dans ton manuscrit. Et je me suis demandé pourquoi tu n'avais pas profité, puisque tu as fait des comparaisons finalement entre le module de la plaque et le module oscillométromètre à différents endroits. Je me suis demandé pourquoi tu n'avais pas profité pour faire des comparaisons avec des modules obtenus au Ponts 3 ou des modules obtenus en laboratoire sur des échantillons ou d'autres types d'essais pour valider en fait tout ça.
We have performed 6 different Panda 3 on the site. Only one has good value information, but the shear wave velocity of this Panda 3 is in good agreement with the MASBB, and the shape of the tip resistant profile is the same that I obtained from the Panda 2. And it's because of that I have not doing the comparison with only one, because I wanted to do a statistical comparison. But it's true, if I have more information from Panda 3, I wanted to do a larger comparison between different methods. That was the point of this part of the thesis. And my main objective was to say that the modulus obtained by the lightweight reflectometers are more or less uncoherent with the values obtained with other methods that were used on the experimentation side.
Je vais passer maintenant sur les mesures plutôt d'accélération, où je suis moins familier de ce type de mesure. J'avais une certaine question sur la prise de mesure en tant que telle. J'avais noté page 107. En page 107, tu nous montres sur la figure de 20, et finalement, la réponse obtenue sur ta voie 1 et ta voie 2. Et je me demandais en fait pourquoi sur la partie voie 1, on avait un bruit comme ça aussi fort qu'on ne voyait pas apparaître sur l'autre voie, et à quoi c'était dû.
In fact, this is not an accelerometer, this is a strain gauge due to the rail. This was used as trigger. I said before that I only recorded trains during 5 months. My problem was that the strain gauge was glued to the rail, was not very glued at some time. It's because of that the noise that you can see in the lower part of the plot. After 5 months, the strain gauge goes wet. And it was used as trigger. Okay. We don't have trigger, we don't have machine.
Si on continue là-dessus, page 127 sur la figure 2.42. Donc là, tu fais une comparaison finalement entre ton accéléromètre et ton capteur LVDT. C'est bon, 127.
J'étais sur la 137.
Figure 2.42.
Oui.
Donc si je regarde le premier graphique, là, où tu fais la comparaison entre ton accéléromètre et ton LVDT, je ne comprenais pas pourquoi au départ tu n'étais pas à 0 sur les deux courbes en fait. Qu'est-ce qui se passait là et comment tu expliquais ça?
Because of the boundary conditions on integration conditions. Because I suppose that it's 0 at the beginning and 0 at the end, and we obtain it's because of that the deflections amplitude are measured as I explained before. But finally, at the end, I measure these deflections of amplitude in the LVDT and in the accelerometer in the same way to be comparable. And then I compare the amplitudes in the figure right here, this one here. Then I have done several filters, water filters, different low pass filters, different frequencies, and I compare with the amplitude of the locomotive and the LVDT and the amplitude, as I explained before, for these deflections.
Alors sur ce traitement de données, en fait, tu appliques finalement des filtres sur ton signal. Tu expliques relativement précisément ta thèse des problèmes de nettoyage finalement aux axes, des différentes choses. Néanmoins, j'aurais aimé avoir ton avis, ou je ne sais pas si tu l'as fait, de l'influence finalement de la fréquence de coupure sur tes résultats. Est-ce que tu as regardé ça et qu'est-ce que ça donne?
Yes. In fact, more than 99% of the deflection amplitude is developed by the wavelengths lower than the axle load for speeds at 200 kilometers per hour. So it's more or less 21 hertz. Then I wanted to avoid all the accelerations that does not give a lot of energy to the system, and that does not develop deflections on the one interrated level. It is because of that I use 25, because the frequency excited by the axle weight is about 21. It's because of that I use 25. In order, when I do that, I'm able also to compare this data. For example, if someone wants to perform a FEM model, because in the FEM model we are not modeling the dynamic interaction sometimes. Only we have this kind of wavelengths.
Page 139 maintenant. Oui. Sur le tableau 2.8, donc tu obtiens finalement des amplitudes assez différentes, je crois, sur la voie numéro 1. Je me souviens plus bien. En fait, tu as fait des essais dans les différentes directions. Et en fait, tu obtiens des différences assez importantes sur la direction. Et je ne me suis pas tellement expliqué ça. Je ne sais pas si toi tu pouvais.
In fact, when a train starts running on a same direction in the rail, there's a formation of small ripples of small amplitude, and the amplitude in acceleration, even stress, is different if we are running on one side, on one direction, or on another direction. It's because of that I only choose same running in the same direction, the regular direction of track 1. In this case, I'm sure that all the ripples are in the same direction, and the conditions are the same, or the results are comparable.
J'avais une question sur l'obtention du module résilient du dumping ratio, notamment sur la SVG, la couche SVG. Donc ça c'est page 151 ou 150, non plutôt 150 pardon. C'est comment tu obtiens finalement sur ces courbes qu'on a figure 263. Tu as expliqué effectivement de manière un peu théorique comment tu pouvais obtenir ton dumping ratio et ton module résilient. Alors autant sur la figure 262 on voit que ça se passe pas trop mal. Autant sur ces courbes-là, on se demande un petit peu comment tu as sorti.
More the accelerometers are distant one to another, worse the vertical strain signal is obtained. And then, but even if it's not so much beautiful as the previous one, I'm able to calculate mainly the resilient modulus in the same way as I showed in this figure.
Beaucoup plus d'imprécision par contre sur ce.
Yes.
Et tu as analysé un peu, on n'a pas réellement de données sur cette imprécision.
When we have done a test, only a test with finite models of Ecole and we obtain similar results as the stress signals and the strain signals. That means that more or less the resilient models will be the same. We obtain the same signals for different axle loads.
J'en viens maintenant sur l'analyse en laboratoire de ta couche intermédiaire. J'aurais voulu avoir ton opinion sur finalement la comparaison des résultats que tu as eu en laboratoire sur une couche intermédiaire reconstituée, donc qui est finalement homogène au sens du laboratoire, et finalement cette couche intermédiaire in situ, qui va être, de mon point de vue, plutôt hétérogène, avec un gradient vertical assez important. Et donc, quel est ton avis là-dessus, sur les résultats obtenus et leur application in situ
That's a very good question, because it's because of that we are covering right now different tests on laboratory, taking into account different volumetric fractions of ballast. Then we are seeing the influence of the volumetric fraction of ballast into a different soil with matrix, using the same matrix soil sphere, performed by Professor We are having one.
Et donc pour le moment, tu n'as pas de, tu n'as pas réellement de conclusion ou de.
Yes, it has to be very important. We have one fraction volumetric at which the inclusion soil starts to be in contact, and all the soil is not governed by the matrix soil, but by the inclusion soil. At the beginning, the soil will be behaving like a ballast, and when we are going in that, it will be behaved as a superfluous.
Ah oui, alors, sur ton modèle analytique, on passe sur le 241. Alors, page 241, tu nous dis que finalement tu trouves un bon agrément entre tes résultats calculés et puis mesurés. Tu nous montres ça finalement pour une valeur de vitesse à 60 km/h. Et moi j'aurais aimé avoir qu'est-ce qui se passe pour les vitesses. Est-ce qu'on a le même type de résultat? Est-ce que
the amplification is governed by the first term of this equation, then the amplification with the speed is governed by that. Then, and we obtain the same evolution as shown in the of the amplitude. We're talking about amplitude in the figure 4.3, page number 234.
Ah oui, j'avais une autre question sur ce modèle, là, notamment sur l'obtention de ta courbe d'atténuation. C'est page 248, je crois. Tu as dit aussi sur la transparence, c'est transparent 29, peut-être. J'ai pas très bien compris comment tu choisissais finalement cette courbe, la courbe C ici. Là,
The first one, the A, is the curve only taking into account the transition layer and the subgrade. The curve B is a curve only taking into account the surface and the interlayer. Then the C is the minimal square curve for parabolic exponential curve for taking into account all the parameters, all the depths.
Sur le point obtenu par une régression par tu l'as précisé ça sur le point? Je ne l'ai pas vu peut-être.
Yes, I think it's in the second paragraph, more or less the fifth line.
D'accord. Et une dernière question finalement. Aujourd'hui, tu proposes d'utiliser ces techniques de mesure finalement de surface pour essayer de retrouver l'effet des trains sur les passages sur la voie. Ça veut dire que tu envisages chaque moment à une échelle d'un gestionnaire de voie. Aujourd'hui, ça va être implanté vraiment de manière systématique, ça va être à certains endroits. Comment demain tu vas être peut-être embauché par SNCF, tu l'es déjà, tu as du suivi à faire, comment tu envisages de mettre ça en place?
Moi, je l'envisage à l'échelle de tout un réseau. I think that could be a very good system to improve the predictive maintenance, mainly, and reduce the human knowledge needs, because right now all the maintenance is very based on the human knowledge. There we have a problem, there we have a problem, we have to measure that. I think that's, I have a lot of ideas.
Et ça veut dire que tu envisages de mettre ça, je sais pas, à des endroits de problème, à des choses régulièrement traitées.
Ça pourra commencer avec ça.
Je te remercie pour ton explication, tes précisions, et puis bravo pour cette conférence.
Merci.
Thank you very much. Now it's my turn. Following the part that was here. So I will put you some questions. The reporters already mentioned the mutual that we have. So I agree with them. I was prepared to ask you what was your participation in this work, because you have a huge experimental field work, you have a huge laboratory work. For the first question, I think the last slide that you present showed you doing the measurement, so I believe that the work was done by you. For the laboratory, the questions remain. So also for you, congratulations, because it's really a huge work. Related with this, I think I agree. I think one of the reporters. One of the reporters, I think, mentioned that this data that you have from the field is really very original data. My question is, how is doing the storage of all this data patrimony that is very important, I guess, for SNCF, that are the owner, but also for the Ecole, for the Ecole de Ponts, because I think with this data, many other theses could be done, I'm sure. You have already some suggestions to analyze the data, and I will come later on it.
How this data is being stored?
Yes.
Okay. So in the same site, we had a computer, and I wanted to send all the files by Wi-Fi, but by GSM, but it was not possible, it doesn't work. And then finally, every 2 weeks, every week, I went to Gerson's site. I was with a USB, I put the USB in there, and I took with a hard disk all the data. We have more than 200 gigas of data, mainly in this computer. No, it was in different countries. Yes. So, yes.
I think that something also very important is the way that how this data is compiled. In other words, after can be easily used, there is a standard way to start.
I have performed several reports to informate any person who is new to this data of how to use it.
So this I think is really a very important aspect. I will start with some general questions like this, and then I will open time. I don't want to time for then to clarify just some questions. Starting with you already mentioned about questions that has already been put by the reporters concerning the banking and models. I think that in your thesis, in the beginning, even if you did quite large state of art related to your work, I think many references, important references are missing. I think I was surprised not to see so much the work of the team of Professor Lamas-Lopez that have a lot of work related with the small strain, damping, and so on. So I think that this is missing in your documents sometimes. If I have time, I will comment on it. But for the people that is less familiar with transportation, you use resilient models. And resilient models is a definition that is more used in transportation, but that many people in geotechnics don't find. So the first thing that we should do is to define what is the resilient model. Can we explain to me and to the jury what is your definition of resilient models?
The resilient models, we are talking about the resilient concept of the.
Is the models that you define here. I mean, you call in your thesis without a very accurate definition. Is why I put you.
The analytical model.
What is the definition? From what is or what is the origin of resilient models?
Resilient models.
If I am a chemical or structural engineer, I don't know what is the resilient model. Right?
The resilient modulus is a given state of material, which is the resiliency of this material when this material is under a given load is loaded and unloaded to remain at the previous loading level. Then, which is the lasting behavior of this material. Then, for example,
The origin of the definition was not. This is why when you, I think that this was convenient, as many people also use the Nationale models, is a way to skip the precision in the definition of the parameters. There are many in the literature. And I think this also was convenient for you because when you do this interpretation in the field, this macro interpretation is okay. I mean, when you use with resilient models in this broad sense, you avoid the discussion, as was already put it here by Professor Gerd. Where you do just this differentiation, then you calculate the strain, and then you can calculate the models if you have also the stress. So this is really, so my question is that when you do this inclusion of resilient models and also of the damping, for instance, the damping that you define is not always not always the same need. And if you go to the definition of the elastic model, because in the chapter where you put elastic models, you put the standard models, you put the equivalent models. So you inside this type, you put some models that are not really elastic models. And then, if you are using the elastic models, the distance, the bending, is exactly introduced because in soils, when you have the elastic regime, you have exactly the bending, basically. So this is, I think, this concept should be very well clarified. Another thing that is another recommendation is that you talk about the field measurements to have the models. I think that you have so nice statement that when you try to correlate, it is always very important that this correlation will be supported by a theory. So nowadays, we have so many numerical tools available that is possible to give a much deeper interpretation of the data in the field. And then you can correlate, supported by a theoretical theory. So I think that this is things that could be improved later with the data that you have in your work. The application, I fully agree, and I purpose of the thesis I understand. So it is quite straightaway. We would not do everything. But I think that in the beginning it would be very interesting just to expose that those with your thesis that they understand what the parameters that you are using, what they mean. Another general question is about your test program and then the test procedure. So you choose some laboratory tools. You decide to use the band elements. You decide to use the VXL test, study, and cyclic loading test. And so when I was very interested on it, when you decided to use two different loadings. Okay. Interested in the results because this is you try to go more close to how is really the load in the field. But I think that it is here one very important thing, mainly when you are thinking of geomaterials that have fines, and mostly if they are plastic fines, because of the viscosity is what I am interested in. Then in this load system, related with this, we have in the geomaterial behavior the very important aspect that you refer in your thesis, but in fact I didn't understand very well, even if your supervisor is a specialist in non-saturated solids. So you many times talk about water content, but you very few times refer to the pore pressure and to the suction. So my question is, what about the drainage conditions? Because the drainage conditions in the red track is one of the aspects in the behavior. So when you plan your tests, you have first to simulate load. I think you did a step, but I think it's something yet not at least referring in the literature that is a very important aspect. That is the rest area. And this rest area is also related with the drainage condition. The results could be very much affected by it. So how do you comment this aspect, mainly of the drainage, and how you take this aspect in your test program?
In the test program, the drainage conditions of, for example, the triaxial tests were draining. The triaxial tests were draining. It is because of that I did not try to measure the pore pressure evolution during the loading as Trin performed before. Because my objective, Trin in 2011, my objective was the first moment to compare the results of Trin with mine. And I did the test with the same conditions. Then the water into the soil, for example, in the saturated case, that is only the case in which we could have positive pore pressures, was not measured because the drainage was open and it was not possible to measure the pore water pressure evolution. But the influence of the suction in the elastic behavior of the soils has been measured for the band dynamics, but it's not shown in this dissertation. But it has been submitted 1 month ago, a paper with Julian and my colleague Tom Wade-Sam to Geotechnique about this subject.
So the interpretation of the test and the test program with the saturated soil, in fact, the drainage were open.
Yes.
So you didn't control, in fact, the development of pore pressure inside. No. Neither if there was water going out from the switch.
No water went out from the.
Never?
Never. And the step-down coefficient was 0.8.
Okay, so it's difficult to give a little more fundamental analysis of these test results because you have to analyze them as we did in total stress first, and secondly, I mean, it's not sure that during 90,000 cycles you keep the same moisture content. This I'm not sure.
At the speed
It will be important in the next programs to take this if we want to do a fundamental analysis of the test results. I think another thing is related with the analysis of results. Sometimes, but I'm insisting a little in supporting the things by the theory. These results that you did the static or monotonic reaction tests, if you do also some compression tests, it would be very interesting to have the analysis of results in terms of the critical state approach, which probably allow you to define the dry and wet side. And we know that in terms of the cycle behavior of the geometrial, it will be quite interesting to know from the situation of the specimens in the dry side and from the wet side how they behave in terms in long term. So this, I think, is something that could be also interesting to consider it. Again, in general terms, when you were looking for the permanent deformation, you were looking from the beginning to the stabilization of the permanent deformation, right?
In order to analyze the cumulative PhD, yes, I need to that the soil is stabilized and no more plastic deformations are developed.
But I mean, all the tests that you carried out, they stabilize with the number of cycles?
Yes, at 90,000 number of cycles, the rate of permanent strength is very low, lower than 0.01%. Then if I do 10,000 more cycles for every loading stage.
Because I mean, for looking mostly for practical terms, for the railway industry, is very much important to know what is the threshold where.
One thing to say about that, in the non-saturated case is different. In saturated conditions, we are right to sterilize the soil, but in the non-saturated case, the deformations are much lower, but they are not stopped at 90,000 cycles.
So you get the stabilization.
No, but it's very slow. It's quite slow, and the difference between saturated conditions and optimal most common conditions are very, very different. It's more than 100 times.
I'm surprised because, as you know, this test procedure that was introduced, in fact, for unbounded materials, that is the ACNOR standard, and there is also the European standard for PXL tests. When we do this multi-stage stress levels, it was the idea, it was to define what was the stable and unstable domain of the material, to define a threshold stress. And I mean, it could be very interesting that in your program you were looking for this aspect, because in that case you could introduce the concept of shakedown. And this is, from my point of view, a very practical concept. If it is theoretical, it has a very nice practical application for the case of materials, geomaterials under the cyclic program. Okay, so I go to some quick questions in your document. One aspect, when you define the different grading of the different materials, you said that you have different fine contents in terms of volumetric percentage, right? Yes. And I saw some grading curves. First, my question is, what is the definition for you of fines? Because you know, in the aggregate industry, they have a definition what is fines. In geotechnical engineering, I have another definition what is fines.
It depends on the domain. But when in this manuscript, this dissertation, when I am talking about fines, I'm talking about the fine regarding to the French standard for the grain size distribution, and all the grain size lower than 18 micrometers.
Okay, so this is geotechnical approach. And what is the grain size that you consider for the sand?
The grain size for the
classification, because you don't know about classification, there are many. You have the French, you have the Ecole classification, there is agriculture, the classification for soils. And I was very surprised, because if you go to your page 167, and you move to different components, when you try to reconstitute your samples, you, for instance, the sand C10. If I look to the grain size, I don't understand why you call sand.
It refers to the industrial name of these products. Because its name is sand, HN, it's because of that. It's not the geotechnical.
It was the same.
Yes.
You call here
specialized is the
but after you call quality. So sometimes there is difficult to understand, but okay. It's a question of rigor in terminology. Sometimes this is missing. But again, I think that this is the lack of rigor that you should use in the thesis. Because this is very confusing. When I look to these gradings, it was difficult for a geotechnical person to understand why these names appear. Okay, so I think I know how to take more time. Someone is saying that I should control the time. Being the president, just one question, the last question. When you listen this figure relating the resilient models, as you call, with the number of cycles and the damping, it is observed that this should be page 227. Yes, is the figure 366. You show that the resilient models decrease with the increase of stress.
Yes.
And then, for the same conditions, you show that the damping ratio decrease with the increase of stress. Can you comment on it, based mainly in what you know from the dynamic behavior of soils?
In fact, it increased. It increased with the increase of the military loading level. The modulus decreased, when we are entering in a non-linear behavior of the soil, and then the damping rate starts to increase. Is the case? The 365.
Yes.
66.
Page 227.
This is because, sorry, because I was looking at the previous one. This is because when I have this question.
Yes.
Here. Then when I give
the other one before. My question is about
no, it's not that. It's because of that. I will explain. Because the amplitude, the apparatus was not simulating well the amplitude that I wanted. For example, here we can see that at different speeds, here, the first one, well, this is simulating the speed at 100 kilometers per hour. These are the cycles simulating train speed of 160 kilometers per hour, and the third one at 200 kilometers per hour. The apparatus was not able to conserve the same amplitude because of the sampling and the loading frequency. And the amplitude was reduced. And it's because of that we obtained results that are not according with the theory of the soil dynamics. Because the amplitude is not correct, even if I compare the test by ignoring it.
I was really surprised. I think what it was really interesting is because we know that it's a well-established between the models and the if they are normalized. And you could do in fact the same, but the trend here is really opposite what we know. So
I think I have put even in the dissertation, but it's because of that.
Okay, thank you very much. I'm sorry to take so much time, but your work is so interesting that I can spend all day.
Thank you very much.
So we move to the next examinator, and I give the word to Dr. Pedro Lamas-Lopez.
Yes.
No? This one is
Thank you. Good afternoon. So, first of all, I would like to greet my colleagues, the jury, and to present my acknowledgement to Professor Junju Gui and the Ecole for inviting me for this journey. It's an honor to share the jury with all of you. I would like also to greet candidate Francisco Lamas-Lopez. I congratulate Francisco Lopez for this moment and wish him success. I will start with a brief general overview and appreciation of the dissertation, and then two or three questions. So the dissertation deals with field and laboratory investigations on the dynamic behavior of conventional and ancient gravity tracks. The topic, in my opinion, is modern and relevant for technical and scientific communities, including regular infrastructures. A relevant and implicit effort was put in the development of the experimental tests, namely in the field. Tests which are always complex with an associated risk, allowing to develop an indubitable top-level database in this specific topic. This dissertation is written in a good English, allowing an easy reading. However, sometimes the text is too much detailed and longer, and in my opinion, it can be written in the way without losing the main aspects that we want to transmit that are very interesting. These aspects. The technical components contribute to the literature, mainly on the topic beyond mechanical behavior and experience. I would like to stress that the contents of the dissertation achieve and supplant the standard for a PhD hour and present a significant contribution for the For sure, for this. Excellent, excellent work. I have some questions, and we can start with a simple question. Regarding here the estimation of the young models, and we can go to page 34 and to other page. So you have here page 34 for equation 1.7. You are trying to estimate the PV2 by correlation. I didn't check the reliability of this correlation. I didn't see so any reference.
This correlation is used by a German standard. There's a German standard that show how this test, the line weight spectrometer test, should be performed. And there's a correlation between the dynamic modulus and the spectral modulus. And I took the equation as the specific in the standard. Okay, yes.
Coming back again to the critical velocity. Regarding the critical velocity here in the page 38. So you started with the discussion about the shear wave velocities, the velocities, and so on, and then you jumped in equation 1.10 to the definition of the critical velocity. I would like to hear you about the suitability of this equation for dealing with this kind of problem.
In fact, this is a simplification of the problem because, as you know, the critical velocity on a track depends on the configuration of all the track and all the elements that are presented on the track. If we are only taking into account, for example, the shear wave velocity in the subway, we are simplifying the problem. And for example, with the formula, the equation number 10 was the first formulation that I have used in 2010. When 2011, sorry, when I started to study.
I just want to see some comments here on text because, in my opinion, this equation gives you results that are very far away from the physics of the problem we are doing at the moment. This is one equation for other kind of problem.
It's based on the inertia of a beam.
Without shear, the stiffness, and so on. So maybe just a comment will improve the text. That's all. So jumping to chapter number 2. Yes. I think chapter number 2 regarding here the tests that we have developed with Panda and then try to estimate the results in page 96. So for me, the results that we have here in this table were a surprise. Not regarding the average value, because I was expecting more or less this value, but regarding the standard deviation. So for the ballast, we have an average value of 127 megapascal, but the standard deviation of 78 megapascal. So if I want to take characteristic value for this computation,
in fact, my main objective was to show that the cumulative distribution function on the test at different tracks was the same for every layer. Then I have not put the evolution that is shown in the page.
I just wanted to put some comment about this value that we have here for the standard deviation, because if you have an average value of 127 and the standard deviation of 78,
the variation is very high.
Very high.
It's very high. Then it's because of that we cannot analyze the panda from for example, from one panda. We need a lot of panda tests, a lot of them, to statistically analyze them. We are not able from one panda to analyze what is happening on the soil. I wanted to show that we need a huge campaign of prospection to give reliable data.
I was expecting to have more or less the problem, of course. More or less were expected. And these transfer other question regarding the estimation of the strength from your problem. So we estimated the strength from the
different accelerometers.
Deformations and integrated deformations. So maybe there are some. You didn't hear what Felix explained the integration process, but I think that is quite classical. I was expecting.
I didn't saw this kind of analysis in literature, but I wanted to show that because when I wanted to do an integration, even on surface accelerometers or inhibitor accelerometers, I found that that's very common. We know that, but there's no so much publications about the deflections under running train or using this kind of. In 2007, the people of Southampton they published some papers about that, but it's not as explained as I hope.
But well, so you are assuming that you have constant strain inside the domain 2 points.
Yeah, it's an
hypothesis, of course. And then for one of the cases, at least for the survey, you are taking the stress in the bottom of the domain. But
yes.
That solution you get it at the same time.
For the second one, yes, in the software, yes.
Yes.
But I show that.
So you have a number string, more or less number. I don't know what means the string, and then you have a stress on the bottom. And then we try to estimate here some stress strain loops. And from this stress strain loops, you got the stress and the strain are characteristics of a point. To measure the strain, the stress in the same point. We know that it's quite difficult to measure strain. Impossible. But at least if the position of the measure of the stress was in the middle, more or less. But in the bottom, I have my doubt about it. But yeah, then you try to estimate here the model, and you obtain very low values. How do you compare these values with the values of your models that you have from the final test? For you,
the main difference is that when we are taking into account these real measurements from the in-situ measurements, they are taking into account the inertia of all the real mass. There's a real mass. The train is.
You have and if you do the inertia increase of the stress, the relationship.
Yes.
Okay, let's assume that we are
more or less plastic. Yes.
So at the end, you are obtaining quite small values for this MR model using these stress points.
Because of that, to answer the first thing about to have the fact or to have the stress sensor at the bottom, I think from the 1.5 meter to 2.3 meters, that is the position of this sensor. There's a low variation of the stress amplitude in this range. The larger decrease of this amplitude appears during the first meter and a half. Then it's because of that I can do this second hypothesis.
It depends a little bit with the track. With the track taking a classical solution is not so smooth. This variation over in this depth. But
then for the second question, it's because of that I have not compared the modules obtained from the test campaign and commercial train analysis with the modules that I have performed in order to obtain the track global stiffness, the modules of each layer. But my objective was to show if there's some evolution of these modules, resilient modules with the speed, not regarding the absolute values, but the relative evolution with a speed assuming the same condition of motion.
But look, if you take, you have young models in one hand, if you assume that you have awesome breaking equal to 0, that's the NER value and the young models are the same.
Yes.
If you have a awesome breaking that is higher than 0, your MR model must be higher than the young model. And you are obtaining a very large difference here on the test, and if you jump to the left, you see again this very, very large difference. I want to see some discussion about this, because at the end of the day, for practical application, which model should be?
Yes.
In your opinion, what is more?
More reliable, the laboratory models.
Yes. I'm not so sure because in the lab you have always.
The inertia effect. It's because of that I was talking about the inertia effect in the measurements.
Just one more question. Well, in the next, we can move to the next chapter and understand. So, in the next chapter, chapter number 4, you made here, or chapter number 3, I'm sorry, you made here an impressive effort with the lab tests and with tracks of tests using these large samples. And you have here the classical justification for this. You are using large, very large samples. I think the sample is 600 millimeters. And you present me here the justification that I was expecting. The reason for using this sample is that you have I agree, of course, with this justification. I just want to your opinion about this, because we have here one situation that is completely different from classical solid mechanics and geotechnical engineering. So we have a sample that is larger than the structure. Now we have a sample that is 60 centimeters height. We have a structure with 20 centimeters.
In fact, we don't mind about the size of the sample because we are seeking to have an elementary volume of our material. Then we are taking material from one point on 40 centimeters of interlayer, and we are doing an elementary volume of this material. Then we are not looking into the size effectively. We are not doing a physical model.
Yes, I share the same opinion. Well, the last question. Here in page 208, I guess. Yes, page 208. I think that the legend of this figure 3.42 is not correct. You have here the damping with the units megapascal.
Was it 203?
208.
Sorry. Yes.
Well, this is the type of. So as I understood from the tests that you explaining here, you apply the loads to a cyclic stress ratio close to 1, right?
Yes.
So you have some tests here where the cyclic stress ratio is very close to 1.
Yes, very even.
So
even
you are very close to
larger. Even larger.
Even larger.
Yeah,
okay.
1.16, I think.
And then you
1.09. Sorry.
You are computing an MR model.
Yes.
But
we
MR
have a lot
models.
It's not a resilient model.
Elasticity, and you are not in elastic domain.
Yes, because we are inducing a lot of permanent deformation during the first cycles. I use mainly this concept of resilient models for the stabilized zone in large number of cycles tests. But in this case, it's true that I was mentioning the second modulus for every stasis loop when I was increasing the lowering deviatory amplitude. And it's because of that, it decreased rapidly for the first cycles, and then it decreased.
Okay, there is an aspect that is very well reflected in the introduction, but not in the literature review, but not in this chapter on this chapter, experimentation, is about the rotation of the principal stresses.
Yes.
So for the permanent deformation, this is one aspect.
It depends. There are some authors that are saying that, like Momoya, Dr. Momoya, like Ishikawa, that they say, or in Southampton, that they say that there's an influence. But I was with the apparatus that I selected to make this experimentation, that is not a physical model, but they said that they have done in Japan, for example, in 2011. And we're not able to induce this kind of simulating the rotation.
We are only with those like of the shear.
Yeah. I would need another hollow cylinder, for example, as if David Connolly is performing very well.
Well, I think it's done. I have more one question that I can discuss after the Viva. So my congratulations for this excellent.
Thank you very much. Thank you very much.
Obrigado, Mr. Chairman. Thank you very much for this very nice and intellectual presentation, Francisco. It was very pleasant to read the dissertation. And, you've performed many experiments in situ with a unique experimental setup. It was quite challenging, I think. Many laboratory experiments, very detailed analysis. Perhaps you could have done a few other experiments on the resonant apparatus just in front of this building at least, but I don't know when during the night or weekend. I don't know. And finally, you've proposed several quantitative methods to analytical approaches. So you try to validate these approaches and to get simple ways to estimate important parameters for the problem. So I have many questions, but I will concentrate on these questions. First of all, you mentioned in your dissertation this wavelength related to the railway system. So lambda wavelength related to the railway system. Probably in the low frequency range, you may have some influence of the trackbed structure on these so-called wavelength related to whether
I totally agree with you. But I was trying to relate each one of the peaks with distance, well, lambda or distance, existing in the train or trackbed geometrical condition. They found that for every train running not only in this site, but also in the site of Moulin-Blanc from the Tesis of Train in 2011, we are always obtaining the same peaks that are in accord with the dimensions of the train. Then in the low frequency range, we will obtain several peaks that are according with the distance of the carriage, the half distance of the carriage, the movie distance, the axle distance. I was focusing on that, but for sure there will be frequencies that will be excited because of the configuration of the trackbed materials.
So probably from one side to another, the location of the low frequency peaks may change.
But they are mainly related to the configuration, the geometrical configuration of the frame. In the low signal. It depends if we are doing transfer function between different layers. It will depend mainly on the mechanical characteristics of every layer.
But we may also have some strong dynamic interactions between the, let's say, substructure and the solid layers.
Mainly, the larger difference in this transfer function analysis will be found in the interaction between the track and the subradio, because it's are the two systems in which we have larger differences. Subradio and track.
I also have a question about the Benderman's experiments.
Yes.
So you consider the travel time estimation for the velocity measurement, but it is not so easy, in fact, because you have many changes in the peak shapes. So did you consider any other method to perform such estimation?
When I performed that with Tom Wade, San, a colleague that has worked with me in this part of the thesis, we have considered 4 different methods to calculate this travel time from one side to another, and the method that was retained was presented by Lu in 1998. Then, using this method, in all the samples, it was able to be determined the distance between the arrival of the excitation to the bottom of the sample. I mean, it was more or less homogeneous for all of them.
So, for instance, did you try such methods as cross-correlation estimations?
No, not correlation estimation.
You mentioned in the dissertation that for the lab experiments, the actuator performance was not so good for increasing the speed. Do you have any perspective?
Sorry,
the actuator performance.
The
actuator.
The actuator, yes. Well, yes.
Do you have any idea for future works?
I was trying several solutions to improve that, trying to variate the virtual rigidity of the actuator, but it was not able to reach the exact amplitude as for trains simulated at 50 kilometers per hour. In that case, all the signal was very well respected, and I have done all the tests of procedure A and B with this frequency, logging frequency, even if the tests were longer in time, but I was respecting the amplitude of each second logging.
Concerning the analytical methods, in part 4, you started with this log spread model, so more or less on the static point of view, and then you try to propagate this log spread model.
Yes.
In the second step.
Yes.
Do you think if you come back to figure 4.7, I think, do you think it may be useful to, in such a propagation model, the next one, considering the propagation, the other, yeah, this one. Do you think it may be important to consider the reflected waves or reflected energy at the various interfaces?
Yeah, for sure. When we are transmitting an energy into this kind of interlayer that is very stiff in the middle of 2 layers that sometimes has lower stiffness, some of the energy will be transmitted and some of the energy will be reflected. And maybe that's a point for the future. be considered in this kind of models. Yes, for sure.
Because in the field of seismology or earthquake geotechnical engineering, such models as cone models may be interesting because you may consider these properly transmitted and reflected waves in cones, so it may be interesting. So just to last quick question. About you've proposed some analytical methods. In the next step, do you think it may be interesting, or it is too complicated, or there are too many drawbacks to investigate numerical methods to analyze such problems, or do you think it is not so efficient when considering the final goal?
My main objective with these analytical models was to give a simple tool for the engineering to calculate easily with not so much parameters, with 4 parameters, the evolution of the trackbed if you are changing the loading conditions or the trackbed conditions. Instead of using, for example, FEM models, or it's only a simple tool prior to make a more deeper approach with all kind of models, more complicated to be implemented in a year.
Thank you very much.
Next is Dr. Jean-Claude.
Thank you, Mr. President. I will speak in French to me some time because there is a lot of people. No question. C'est un plaisir. Tout le monde a dit avant moi, la grosse difficulté du travail, c'est la partie in situ et la partie laboratoire. Je reviens rapidement, ça va être très long, j'ai fait des choses à faire avec les collègues de la SNCF. Mais concernant la partie in situ, j'ai participé, donc je peux le dire à tout le monde, on était sur le terrain, c'était au mois de novembre, c'était un week-end, on travaillait la nuit, et on a dormi quelques heures, et on a dormi, c'est dans la voiture. Donc c'était très très difficile. C'est vrai que j'ai pu apprécier effectivement toutes les qualités, l'autonomie, il faut être assez robuste. J'ai oublié de préciser qu'il n'a pas dormi, parce que je pense qu'il était stressé par le positionnement des capteurs, parce que c'était un marché, tout est posé, des choses. Ça, je pense qu'il a souffert, parce que c'est peut-être un empêché de dormir. Il y a peut-être une autre chose, mais
non, c'est pas revenir dessus. Merci beaucoup, Yann. Et c'est vrai, ces jours-là, c'était dense. On a travaillé pendant 24 heures, un peu plus même, depuis la coupure. On avait 30 heures. Et on a fait tout d'un coup. Donc, au bout de la journée, une fois que tout marchait, je suis arrivé tout endormi dans la voiture, parce que je pouvais plus. C'était génial. On a vu le résultat et ça méritait la peine.
oui, c'est plaisir pour ça marche.
Oui, surtout ça.
Deuxièmement, sur le PHD, on a aussi un outil assez difficile à montrer qu'il y a certaines limitations, mais on a aussi assez souffert parce qu'il a fallu modifier certaines choses, on a des problèmes de capteurs, on a une chose qui a été très découverte sur l'évolution du matériel, sur vérification du développement des capteurs. C'est quand même très agréable en fait. C'est très agréable de travailler avec les. D'abord sur le plan humain, c'est quand même important sur le plan humain parce qu'on peut quantifier des cours, mais sur le plan humain, quand c'est facile à
Merci beaucoup.
Allez-y, si vous voulez quand même remercier toute l'équipe technique de notre laboratoire, parce que bon, sans eux, on a certaines choses qui ont été possibles. Merci.
Merci.
Thank you very much. So we will
move to the next one, examinator, now from the industrial side, from the SNCF, Monsieur Nicolas.
Thank you, Mr. Chairman. As Jean-Claude Anka will speak in French, je rejoins ce qui a été dit sur l'aspect scientifique. Il y a eu un travail considérable de fait. On se posait quelques questions sur les essais triaxiaux qui ont été réalisés. Tu as apporté les réponses, notamment sur la nature des signaux. Je rejoins effectivement Jean-Claude sur l'instrumentation qu'on a réalisée. Bon, on n'a pas eu le barbecue parce qu'on a tout mis dans l'installation des capteurs, on n'a quand même pas pu faire le barbecue. Une petite réserve. Malgré ça, vraiment, tu avais le coutume de le dire, je pense que ce n'était pas galvaudé, c'est une des plus grandes instrumentations qui a été faite sur un réseau ferré. Les résultats qui en sont sortis sont satisfaisants. Je rajouterais une autre qualité, c'est ton dynamisme. Tu sais aussi fédérer, donc je pense que tout ça s'en ressent dans ton travail. Maintenant, pour ce qui est de la partie industrielle, on a commencé la thèse avec un objectif qui était de voir l'effet dynamique, l'effet des circulations et d'augmentation de circulation sur le comportement du prochain intermédiaire. Les figures que tu as pu montrer et les résultats qui viennent dans ta thèse montrent que tu y as répondu. On est maintenant en capacité d'affecter quelques conditions dynamiques lorsqu'on va augmenter la vitesse. Tu as développé deux modèles qui sont repris là et qui doivent être confortés maintenant et voir si on peut les transposer à d'autres sites. Ça, c'est vraiment important. Et voilà. Et enfin, tu as pu, en se basant sur tes connaissances et tes capacités scientifiques et en perdant pas de vue l'aspect industriel, proposer aussi quelque chose qui est facilement duplicable et industrialisable, parce que c'est sûr qu'on ne fera jamais 50 trous dans une plateforme pour regarder le comportement dynamique qu'elle peut avoir. Mais par contre, voilà, tu as été en capacité de proposer des instrumentations légères pour répondre aux objectifs, aux questions. Donc, merci pour ton travail et bonne continuation.
Merci beaucoup.
Thank you. We continue in the industrial side, and now we move to the invited members. And I asked Sofia Costa-Aguiar.
Thank you, Mr. Chairman. Thank you, Francisco, for this presentation, very clear and concise. I would like to acknowledge the members of the jury for being here today. It's an honor for SNCF to share our topics and our problems with such an honorable jury, and a special word to the reviewers for their meticulous work and precisions and comments which enrich the rest of the research of this room. I would like also to thank you, Jean-François Soublat, for having accepted to be part of the Tesis committee and share with us our periodic meetings. And it was an honor also to work with you. And I will not ask questions to Paco because I've been doing that for 5 years. So we have enough. Even though I would like to give some words about the work and the context, we have all talked about the challenges of renewal works and classical renewal program and increased capacity. And it's a real challenge for us at Zoom. And to push forward the knowledge and the limits of our knowledge of the behavior structure is really important. And so we are doing this by promoting an innovation and research projects. And for me, the work which was presented today, it's a very good example of this scientific partnership, a long duration partnership with SNCF. And this work is the fruit of dedicated work, but also the close collaboration between the teams, because it was very important to have someone to make the loop between industrial motivations and scientific motivation. And Paco was the person who has done this work, and he puts a lot of passion, energy, and dedication to it. So I thank you for that. And a rich part of this 5 years was to see Francisco to grow scientifically and personally. Also, we have seen his efforts and the dedication he put onto his work and his pressures, and it reflects the quality of the work, reflects the dedication he put on it. So I would like also to underline the fact that he always wanted to find new solutions and new paths to answer the questions and the problems that we encounter in the work. And we have a lot of problems and questions. For example, the problem that we have in laboratory. He seeked to go until the end of the questions in order to find a solution, even if it could put into risk the experimental program we wanted to do with this work. So I think this is the scientific honesty is very important skill and something that he will continue to use in his professional life. So it's very important. Thank you. You put a lot in this work, so I just have to thank you. And you open a lot of doors to continue to work and to innovate. So for SNCF, it's very rich because, as Antonio and the other members of the jury said, you use either the data and the methods developed in your other works and other investigations. So I'd like to thank you very much and congratulate you and wish you a very fruitful professional life after this moment.
Thank you very much.
The next one is Dr. Chaussées.
Merci. Alors, je vais d'abord expliquer pour à la fois le travail que vous apportez, ainsi que cette présentation didactique très très riche et qui montre toute la complexité de mon travail et, in fine, je pense apporter des réponses à ces problématiques que tu as soulevées. Il faut combiner beaucoup de techniques différentes, beaucoup d'approches et être vraiment pluridisciplinaire. Et ça, c'est quelque chose que je trouve tout à fait. Mon travail, en tout cas, a fortement valorisé et nous apporte beaucoup. Sophia, je pense déjà dit beaucoup de choses. Moi, ce que je voudrais rajouter, c'est qu'on est réellement attaché à la production de connaissances en général dans le cadre de différents projets de recherche. Et tu fais partie, et les résultats de travail montrent déjà d'autres doctorats qui sont en cours ou bien d'autres études. Ça, c'est vraiment important que le sache aujourd'hui. Ensuite, grâce à mon travail, déjà, on a des éléments pragmatiques à donner à des études ou bien pour essayer d'alimenter des référentiels existants. Donc, ça, c'est des choses qui sont, je pense, très bien dans le cadre industriel, d'arriver à extraire de l'ensemble de ces informations-là des choses pragmatiques pour nous. Et ensuite, un dernier point qui concerne la valorisation à la fois de l'instrumentation, mais des données d'entrée. Ce que tu nous permets aussi, grâce à ton travail et grâce à l'effort que tu as fait dans ton enthousiasme et la réussite en fait de mettre en œuvre tout cela, c'est de montrer que les données d'entrée sont indispensables pour donner des recommandations. Ce que je dis paraît évidemment ici, mais quand il faut justifier auprès de projets concrets, il faut faire cet effort-là avant de les lancer, c'est pas si évident. Et en fait, tu dois contribuer à nous montrer que c'est valorisable, que c'est intéressant et que ça peut permettre effectivement de proposer des solutions qui puissent assurer la pérennité des travaux. Voilà. Donc merci pour tout ce que tu as fait et bonne continuation sur tout ce que tu as fait par nous.
Merci. Thank you. The next one is Dr. Anne Tang, return to the Ecole.
Merci, Monsieur le Président. Je vais parler très long. Juste pour je vous rejoins d'abord dans les autres membres du jury pour féliciter pour le travail, qualité du travail, et aussi un plaisir pour vous présenter l'événement. S'il y a des mots à retenir, parce qu'il y a des choses qui ont été dites, mais c'est plus de mots à retenir pour moi, la qualité du travail. De mon côté, c'est vraiment pour lui. Il y a une thèse. Et deuxième chose, c'est l'enthousiasme. Je pense qu'avec ça, on peut faire tous les plans d'équipe de traitement qui essaient de suivre en continuation. Merci.
Merci beaucoup.
The next one is Dr. Jean Cabot.
Okay, thank you, Mr. President. Almost everything has been said on the work, so probably also very short. So, congratulations for your work, presentation, and everything. I must say that it has been a great pleasure for me to participate in the supervision of your thesis. A very interesting, very important issue for us to the numerous progress meetings we have had with SNCF and very interesting discussions, in particular the scientific interaction testing and scientific behavior, famous routine. I must also say that I have been quite impressed by your working capacity, the energy displayed or power displayed in your work, and through this, every say that showed all along the PhD, a real locomotive, which is very consistent with the subject of the thesis. Also, our discussions were always very fruitful. You would always take into account the advices, recommendations, and work again and again. And this was very good behavior. You have so very good contact, very pleasant friend, strong character, but Spanish character, southern Spain character, which I really appreciated. I think you have brought a very important contribution, I think, to a sincere issue on the upgrade of traditional railway lines. Of course, and I would say fortunately enough for researchers and students, there is still quite a lot of work ahead in order to go even further, but this is not normal. This is for the successor. Again, congratulations for your work.
Thank you very much. Thank you.
Okay, we move again to the industrial side, and I give the word to Mr. Alain Robinet.
Merci, Monsieur le Président. Estimé au Paro. Je voulais situer un petit peu le contexte très rapidement, mais de dire que ce travail, ce excellent travail, c'est le troisième pavé d'une route qui nous-mêmes, on a construit avec l'école des Chaussées, et qui nous-mêmes permet la connaissance de la notion. Et puis, surtout, de notre connaissance sur la couche intermédiaire. C'est une troisième étape, c'est une troisième pierre. Il y aura d'autres pierres en construction, je pense. Les deux premières pierres avaient permis de défricher, de beaucoup avancer. Là, cette étape est importante, parce que là, on arrive à des outils, on arrive à des méthodes de mesure, d'acquisition de données, on arrive à des méthodes de modélisation. On commence à toucher plus, à avoir un peu de clair dans nos démarches. Et puis, la démonstration, c'est montre un peu des développes de la situation, créative. T'as pas peur du travail, t'as pas peur de la nouveauté, t'as juste un petit peu peur des serpents.
Oui, et essayez de tout faire pour que les serpents.
Donc,
merci beaucoup.
Thank you very much. Now we move to the director of the thesis, Professor Richard please.
First of all, I would like to thank and also remember for your interesting and constructive comments, remarks, and suggestions. We will improve, of course, the investigation based on your comments and also your report, of course. And hopefully, improve our official work. We will do better. And so many things have been said. But I don't want to repeat. I have been learning about the quality of the presentation of the huge volume of work. And also just add one point. So if I as you can see from this work, we have it's a very variable. We have a huge variability of work nature. You have laboratory tests and different technology. We have field including very hard instrumentation work in the core of the world help by people like Jean-Paul and Nicolas, and also other SSF colleagues. And also, so I want to just try for one quality of I think this work for me it's a very political sense for me. I'm very proud of the work of course of people also. I'm proud because I think he's the only person who can do that. Because it's so, even me, I cannot think I can do that for myself. Because you can see, so with all the quality, human quality, and also the scientific quality and condition. So he succeeded to manage this scientific work by have a good relationship with different people, including the member of the steering committee, Professor. For example, I would like to thank the steering committee composed by the colleagues from SSF 4 people. So I'm achieving alliance of young people, and also my colleagues as I invested in Ecole, to Jean-Paul, Min and Jean-Paul, and also of course from IFSTA and Jean-François. So he was in very well surrounded, but it's also a difficulty to understand everybody. It's not a big hard. You can have many ideas how to take profit of different ideas. So it's not easy, I think. For me, it's very quite difficult. So it's I think that shows your a very high quality of management. So it's not so easy. And the second thing I want to add, I don't want to repeat things. So in addition to the solution we have brought to the scientific spheres and also to the industry, he didn't forget to publish. So you can see. So from here now, we have submitted or published 19. So there are 3 others in preparation. We have a very good application to the industry, but for the academic aspect, also very high level. And so it's very distinguished. Thank you. Yeah. And I don't want to just normally the French tradition allows the supervisor to complete the response to the question of the jury members. But I have realized I have nothing to complete. They defended it so well, but I have nothing to do. Just one. It was easy to quite easy for me. But another thing the tradition wants me to do is just to recall your education. So you finish your study in Spain, and then you have Paris, come to Paris for a master. And after the master, you wanted to do a PhD. So I think I have been very lucky to because he was selected, not by myself, by Nicolas and Sophia. So he said, okay, what will you do? So he took me PhD. Okay. But finally, I realized how lucky I am. So thank you very much, Nicolas and Sophia, for this gift. So, so thank you very much, Marcos.
Thank you very much.
It has been a good pleasure for me to work with you. I think how we will collaborate. Continue, sure. For the remaining 2 years. Good passion.
For sure.
Okay.
Thank you very much.
Okay, thank you very much. I think that formally I should ask to the audience, the participants, for those that have the PhD degree, if someone wants to put any question, and I use this opportunity to give my greetings for you. This is a public reference, so it's always nice to have people around. So, anyone want to put a question, please? If not, I think we conclude this defense. I think that in behalf of the University of Paris and the doctoral school, I should thank all the members of the jury for this cooperation, and I can repeat the institutions, KU11, starting with this order, Université Blaise Pascal, of course, Paris, University of Minho, University of Porto, IFSTAR, and of course, I think very important here is the industrial partner SNCF. There is a lot of members representative of this, and I think this was a big challenge to achieve this work as mentioned. I think all of the members agreed on it before anticipating the decision of the jury that we will go to it. I also want to congratulate you for your performance during this exam.
Thank you very much, Professor.
Thank you. We close this, and we came again to announce.
Pour proposer qu'on fasse ici, et je demande l'audience.
Okay.
Merci beaucoup.
Thank you to attend.
I close the computer. Ustedes hacen el streaming. Donc, ya está.